welcome to the deep dive.
Yeah.
We're going to be unpacking some really cool research in the world of AI, specifically how people are using something called generative data augmentation to potentially boost the accuracy of image classification.
Yeah.
Think of it like, giving AI a supercharged training regimen, but instead of pumping iron, it's all about synthetic data.
That's right. And the source material for this deep dive is a paper called Synthetic Data from Diffusion Models Improves ImageNet Classification.
All right, so let's break this down.
Okay.
ImageNet, for those who haven't encountered it before, it's like the ultimate visual encyclopedia for AI, right? It's this massive data set of millions of labeled images used to train and test image recognition algorithms.
That's the gold standard for benchmarking image recognition models.
Exactly. So this research is all about improving how well AI systems can classify images in ImageNet, but with a twist. Instead of relying solely on real-world images, they're exploring the power of synthetic data, or images, generated by AI itself.
And that's where these diffusion models come in.
Diffusion models.
Yeah.
All right. I got to admit, the name sounds a bit intimidating.
Okay.
Can you just kind of demystify that for us a little bit?
So imagine you have a pristine image and you slowly start adding noise to it until it's completely obscured.
Okay.
Like a beautiful landscape fading into static on an old TV screen.
Okay.
A diffusion model works in reverse. It learns to take that noisy mess and gradually denoise it step by step until it reconstructs the original picture.
Okay.
And in the process, it essentially learns the underlying essence of what makes an image, giving it the ability to create new ones from scratch.
So it's like learning to paint by first understanding how to erase.
Yeah, exactly.
That's fascinating. But what makes these diffusion models so special compared to other methods for generating images?
Okay.
Like, we've heard about GANs and things like that.
Well, for one thing, they're proving to be more stable and efficient than GANs, which can be quite temperamental to train.
Oh, really?
Diffusion models tend to produce more consistent and realistic results without those weird artifacts that sometimes pop up with GANs.
Interesting. So we have these diffusion models that can create images from scratch.
Right.
How does that help us classify images in ImageNet?
So the researchers focused on a specific text-to-image diffusion model called Imagen, developed by Google AI.
Right.
And what they wanted to do was essentially train Imagen to be an expert in ImageNet classification.
Ah, Imagen. I remember seeing some of the images that it generated, and I was just like mind-blowing. It's like it could conjure up any image you could describe in words.
Right.
But how do you go from generating cool pictures to actually improving image classification?
Well, ImageNet has very specific categories, right, and ways of depicting objects.
Okay.
So it's not as simple as just giving Imagen a text prompt like golden retriever and expecting it to churn out perfect ImageNet-style images of golden retrievers.
Right.
They had to fine-tune the model, essentially give it a crash course in the visual language of ImageNet.
So they fine-tuned both the base model and the super resolution models within Imagen on the ImageNet dataset.
That's right.
Okay.
They had to make sure it understood the subtle differences in how those categories are represented.
That makes sense, but how did they test if these fine-tuned images were actually any good? Did they just eyeball them?
No, they went beyond just eyeballing them.
Okay.
They used two standard metrics to evaluate the visual quality of the generated images. FID, which stands for Fréchette Inception Distance, and IS, Inception Score.
Okay.
FID measures how similar the distributions of generated images are to those of real images.
Okay.
While IS focuses on the quality and diversity of the generated images.
So what were the results? Did these ImageNet trained images pass the test?
They did. The fine-tuned Imagen achieved state-of-the-art results in both FID and IS.
Wow.
Outperforming previous models specifically designed for ImageNet.
Okay.
It was a clear indication that their approach of pre-training on a massive data set, followed by targeted fine-tuning, was incredibly effective.
That's impressive. It sounds like they've created a model that can generate, top-notch ImageNet-style images.
Right.
But the real question is, can those images actually be used to improve image classification accuracy?
Absolutely.
That's the ultimate goal, right?
Right. FID and IIS are good for assessing visual quality, but they don't tell us the whole story.
Right.
To really gauge the impact of the synthetic data, we need to look at a metric called SciAS.
SciAS, the real test.
Yeah.
What exactly is SciAS and how does it work?
CAS is a metric that cuts to the chase.
Okay.
It measures how well a classifier, trained only on synthetic data,
Okay.
performs on the real ImageNet test set.
All right, so it's like a blind pace test for AI, essentially.
Exactly. Can the model trained on the synthetic stuff perform as well as one trained on the real deal?
I'm on the edge of my seat.
Yeah.
What were the results? Did the synthetic data pass the test?
This is where it gets really intriguing.
Okay.
The researchers trained a standard image classifier, ResNet 50, using only the synthetic images generated by their fine-tuned ImageNet model.
Okay.
And then they set this classifier loose on the real ImageNet validation set and measured its accuracy.
Okay.
And the results were groundbreaking.
Groundbreaking, okay.
The fine-tuned ImageNet-generated data led to a new state-of-the-art CAS score.
So are we saying that models trained purely on synthetic data are now as good as those trained on real data?
Not quite yet.
Okay.
There's still a gap.
Okay.
But the gap is closing.
Okay.
Especially when using those higher resolution synthetic images.
Okay.
The ones with 1024 by 1024 pixels.
So the higher the resolution of the synthetic image, the better the results.
You would think so, right? But here's where it gets even more interesting. Yeah, we were talking about how higher resolution synthetic images seem like they would lead to better results.
Right.
But there is a twist.
Okay.
When the researchers started experimenting with augmenting the real ImageNet data with these synthetic images, they found something quite surprising.
Okay.
The benefits were actually more pronounced when using the smaller, lower resolution images.
Wait, really?
Yeah.
That's counterintuitive. You'd think more detail would equal better results.
It does seem that way, doesn't it? But think of it like this. ImageNet is already incredibly detailed and diverse.
Okay.
For a higher resolution synthetic image to truly add something new, it would have to be practically indistinguishable from a real image.
So maybe those smaller, lower resolution images work better because they're acting like a special type of training. Almost like adding a bit of blur so the AI has to focus on the bigger picture and not get bogged down in tiny details.
That's a great way to put it. It could be acting as a form of regularization.
Okay.
Preventing the model from overfitting to the real data.
Okay.
And forcing it to learn more generalizable features.
Okay.
Kind of like a weightlifter varying their routine to build more balanced strength.
That makes a lot of sense. And this research isn't just changing the game for image classification. It's also challenging how we evaluate those image-generating models in the first place.
You're talking about FID and IS again?
Exactly. There's been this idea that FID and IS are good at judging how realistic an image looks.
Why?
But not necessarily how useful it is for a task like image classification.
And this study really throws a wrench in that assumption.
Right, because the fine-tuned ImageNet model not only got top marks in FID and IS, but it also smashed records in CAS.
Yeah.
That strong correlation suggests that maybe we need to rethink how we view FID and IS, at least when it comes to these powerful diffusion models.
It definitely calls for a closer look. It highlights the fact that AI research is constantly evolving. What we think is true today might be challenged tomorrow.
Which is what makes it so exciting.
Yeah.
But let's get back to this idea of generative data augmentation for a minute. I'm curious about the practical implications. We talked about how it can help when you're dealing with limited real data.
Yeah.
But what are some real-world scenarios where this could be a game changer?
Think about medical imaging. Imagine you're trying to train an AI to detect a rare disease. But you only have a handful of confirmed cases to work with.
That's not a lot to go on.
Exactly.
Right.
But if you could generate synthetic images of that rare disease, suddenly you have a much larger and more diverse data set to work with, potentially leading to earlier and more accurate diagnoses.
That's incredible. And it's not just about quantity, right?
Yeah.
Synthetic data can also help address issues of data diversity. What if you're training a self-driving car system and you need it to handle all sorts of weather conditions, but you haven't been able to collect real-world data on snowstorms in Arizona?
You're catching on. Using a diffusion model to generate synthetic images of snowy Arizona roads could help train the system to be more robust and adaptable, even if it's never actually encountered those conditions in the real world.
So synthetic data augmentation isn't just a band-aid for limited data. It's also a way to create more comprehensive and balanced data sets, even when you do have a decent amount of real data to start with.
Precisely. And it's not just limited to image classification. This technique could be applied to all sorts of tasks, like image segmentation, object detection, even video generation. The possibilities are vast.
My mind is officially blown. But before we get too carried away, we should probably address that unexpected finding about the resolution of the synthetic images. It's still bugging me that the low-resolution images were more effective when it came to data augmentation. Why would that be?
That's a great question. And honestly, the researchers are still figuring it out themselves. They have a few theories, though.
Yeah. Okay, let's hear them.
Well, one idea is that those smaller images, with their inherent lack of superfine detail, might actually be helping the AI models avoid overfitting.
Overfitting. Remind me what that is again?
It's like when you study for a test by memorizing the answers.
Okay.
Instead of understanding the concepts.
Yeah.
You might ace that specific test, but you won't be able to apply that knowledge to new problems.
So it's like the model is getting too focused on the specific details of the training data.
Right.
Instead of learning the broader pattern.
Exactly. And those lower resolution synthetic images with their slightly blurry nature might be preventing the model from getting too fixated on those tiny details, forcing it to learn more generalizable features instead.
Interesting. It's almost like those smaller images are acting as a kind of training tool.
Yeah.
Helping the model develop a more robust understanding of the visual world.
That's a great way to think about it. And there's another interesting observation from the paper that ties into this. The researchers found that as they increased the amount of synthetic data used for augmentation, the performance gains started to level off, especially with those higher resolution images.
So there's a point where adding more synthetic data doesn't really help anymore.
It seems that way, at least with the current generation of diffusion models.
Okay.
It's like adding more flour to a cake recipe.
Right.
At some point, you've got enough. And adding more just makes it dense and heavy.
That's a great analogy. So what does this all mean for the future of synthetic data and image classification?
It suggests that while we've made incredible strides, there's still room for improvement.
Okay.
Maybe future diffusion models will be able to create synthetic images that are even more realistic and diverse, pushing those performance gains even further.
That's exciting to think about. But even with the current limitations, this research has opened up some incredible possibilities.
Absolutely. It's shown us that synthetic data can be a powerful tool for boosting the accuracy of image classification models. Yeah. Especially when we're dealing with limited or imperfect real-world data.
It's like giving AI a superpower.
It really is. Yeah. And the potential applications go far beyond just image classification.
Right.
This technique could revolutionize fields like medical imaging, self-driving car systems, and even creative industries.
It seems like we're at the dawn of a new era in AI.
Yeah.
And it's fascinating to think about how these advancements will shape our world in the years to come.
Well said. It's a reminder that AI research isn't just about building bigger and more complex models. It's also about finding creative ways to generate and leverage data, both real and synthetic, to solve real-world problems.
And who knows what incredible breakthroughs await us just around the corner. This has been an incredible deep dive.
Yeah.
Thanks for joining us on this journey of discovery.
Thanks for having me. It's always a pleasure to delve into these fascinating topics.
And to our listeners, thanks for tuning in. We hope you found this deep dive informative and thought-provoking. Don't forget to subscribe to The Deep Dive for more explorations of the amazing world of AI. Until next time.